Hello class, this is CSE-5250, section 61, week 12, though this is the video meant for week 11, fall 2024. So there was quite a few things that I forgot to put in the last set of slides, and on top of that, there were a few bugs in the programs I was trying to demonstrate. So here, hopefully now I've fixed all the issues, so now we can get to, programming with OpenMP more. Alright, so let's do a little bit of a recap. So we began with working with OpenMP, and this is just another library for making parallel programs, much like with pthreads, except that pthreads is a little bit you need to remember to write certain functions or else the program will not work. You need to remember to fork the main thread into several threads, and then you have to remember to call join to make sure everything joins back together properly. OpenMP makes this programming a little bit easier in that we don't need to call these fork and join functions anymore. Rather, the compiler is gonna do that for us. So basically, OpenMP has a few things that makes it easier for us to write parallel programs. That is the point of OpenMP after all. So we began with writing a program that implements the trapezoidal rule. So this is a thing in calculus in which we estimate the area under the curve by approximating the area as a series of trapezoids, and then we just sum all the trapezoids together. So the base code for that was this, and the reason why as to why that is as follows. Here we are. So we have some curve, call it f of x, and we want to find the area under the curve bounded by endpoints a and b. If we want to calculate this area as a as a bunch of trapezoids, we consider one trapezoid bounded by endpoints ai and aj. We take out this trapezoid so we can look at it in greater depth. It has a left edge and a right edge. The left edge is defined by, well, since this trapezoid is bound by endpoints AI and AJ, we can calculate L as being f of AI and R as being f of AJ. So we have heights L and R, the left and right heights, and we also have a width. We define the width as being whatever the length of A and B is divided by the number of trapezoids we are cutting this area into. So we're cutting it into n trapezoids, so I guess there's one thing missing here, and that is W is B minus A over n, where n is the number of trapezoids. So with that, we can calculate the area of this one trapezoid as being the average of L and R. And the average of L and R is basically L plus R all divided by 2. But then we multiply it by the width of our trapezoid. So now we have that formula. We can express the area as a sum of individual trapezoids' areas. So it's this summation here. So from I equals 1 to n, we have Li plus Ri, and then multiplied by W over 2. We can expand this sum as follows. So we can expand the sum, so it's going to be L1 plus R1, and then L2 plus R2. But we can also factor out the W over 2 here, so we now expand this sum to be this here. So W over 2 times everything that's in the parentheses. So that is L1 plus R1 plus L2 plus R2 plus dot 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 plus Ln minus 1 plus Rn minus 1 plus Ln plus Rn. One thing to note about this entire sum is that the right edge of a trapezoid is the same as the left edge of the trapezoid that comes next. So here, R1 and L2, they're the same value. So is R2 and the not shown here, L3. Same with the not shown here, Rn minus 2 and Ln minus 1. And finally the same with Rn minus 1 and Ln. Those pairs of values, they are the same value. So what we can do is this. We can take this value and take this value, put them here, and then we can express everything else here as its own summation as follows. So we can express this as being the left edge or the right edge. For the sake of consistency, I'm just going to say we are adding 2 of the left edge. So now we have this brand new summation. From I equals 2 to n, we're adding 2 of the left edge. We can then redistribute this w over 2, and now we have this w times the left and right edge all over 2. Oh, and by the way, this L1 and Rn, those actually correspond to A and B, because this is the left edge of the first trapezoid and the right edge of the last trapezoid. So we redistribute this, so now we have this. This is just extra stuff that I have to calculate before we calculate this. But we can take a look at this and realize that when we multiply this sum here with w over 2, the 2 in here can be factored out of the sum, and then it cancels out with the over 2 over here. So that's why when we distribute it, we get this plus this, and the 2 is canceled out, so it's just w times this new summation. We can factor out the w once more, and now we have this. This is a different way of expressing the sum of our this is just a different way of expressing how our summation program will work. So it's the leftmost edge plus the rightmost edge, the average of that divided by, so it's the average of that, and then we're gonna sum all the left edges of all the other trapezoids, and then we're gonna multiply everything by w. That is what's going on in here. So confusingly, the width of the trapezoid is expressed using h, but here we have the initial value of our approximated area under the curve. This approx is what this is. Actually, it's this, because we're multiplying everything by w last. So this is this, and this for loop is this. We add this with the result of our for loop, and then we multiply everything together with w. That's what this approx time equals h times approx is. That is multiplying everything by the width of a trapezoid. So that's what we've been doing so far, and that's just to clear up any confusion as to why is this code written this way. It's to eliminate any redundant multiply by 2 and then divide by 2. So the multiply by 2 and then the divide by 2 cancel out. Math is full of cancel culture, but that is to be expected. Anyway. So we began with our quest of writing an OpenMP version of the trapezoid rule. We began by starting off with using the pragma OMP parallel directive. We wrote our trap function in such a way that it accepts 4 arguments: the left endpoint, the right endpoint, the number of trapezoids, and a pointer to the global result. The global result is our area under the curve. parallel section such that every function calls trap, and then it does some calculations and adds its sum to the global sum. So basically, what each thread is doing is it's doing a portion of the work here. So we, instead of finding the area under the curve, we instead find the area of several portions under the curve and then add them all together. So each thread is calling trap, but it's only calculating a portion of its share of trapezoids. This does, however, require a critical section within the trap function, and it is this. So each thread is calculating its portion of trapezoids. It's basically all the same rules as with this from A to B, except instead of A to B, it's some portion from A to some intermediary value, or some intermediary value to some other intermediary value. The rules are the same. It's just that now it calculates its own result and adds it to the global result. We cannot do that without having a critical section, because if we did not have a critical section, we'll have a race condition and we'll get bonkers results every time we try to run the program. Variables in OpenMP have either shared scope or private scope. So basically, with OpenMP, threads may have variables that only that thread can access, that is private scope, or threads may have variables that other threads can access, that is shared scope. One of the key things here is realizing the scope of each variables. Is this shared or is it private? But before we get to that, there is one other thing that we can do with our program, and that is simplify the program by introducing what is called a reduction clause. This is where we, here in a reduction clause, we declare two things: a reduction operation and a reduction variable. A reduction operation is something that we do repeatedly onto some reduction variable. So if you want to implement a reduction variable, we're gonna make a few changes here. Here, instead of the critical section being a part of the trap function, now it's moved to the main function, because now we write the trap function so it doesn't require having the global result be passed in. So now, on top of that, the trap function also returns a value that is the local area for calculated by that thread. So every thread is now calling trap, and then it's going to add that return value to the global result. However, this code is inefficient because of where the trap function is being called. It's being called within the critical section. That means every thread must wait its turn to call trap and then add it to the global result. If we can separate those two operations, say every thread can call trap, no problem. But it's the critical section of adding the return value to the global result. That is the critical section. That is resolved in this slide here. So we calculate my result as being the return value of trap. Every thread can call trap, no problem. Every thread can call trap at the same time, no problem. It's the only problem is adding my result to the global result. That is the critical section. We can only have one thread do that at a time. So because we have something happening to global result repeatedly, we can say that global result is our reduction variable, and addition is our reduction operation. So we can simplify our code even further. So instead of having a critical section, we have this. So pragma OMP parallel num threads thread count, and then we have a reduction clause added to our code. So we are basically repeatedly adding the return value of trap to our global result. Our reduction variable is global result. Our reduction operation is addition. So this works too, and It's a few lines of code fewer than this implementation here. No more critical section. It's all handled by the reduction clause. We left off right before we were going to look at the parallel for directive. For this to work, I need a whole new set of slides. So here it is, and these are expanded from the last set of slides. In fact, this is an updated part 2. So I'm gonna have to update it on Canvas, but here is where things get interesting. This is where OpenMP becomes really powerful, in my opinion, where we can take a serial program and make very minimal modifications, and boom, it's already parallelized. There are some caveats I have to talk about as well. We'll get to that in a little bit. So first, we need to consider the trapezoidal rule program without any parallelism at all. So this code and this code, those are two parts of the same program. It is the trapezoidal rule function. It is the trapezoidal rule program, no parallelization. How do we make it parallel from here? By doing this. For the trap function, we need to add in a thread count because it's within the trap function that we're going to have our parallel for loop. So we need to pass in the thread count so the program knows how many threads to use. We also have to parse the thread count from a command line argument. So here we go. So now that our trap function is accepting 4 arguments again, that 4th argument is the thread count. We have to parse that from a command line argument before we can even pass that into the call to the trap function. When the function is called, it's going to take thread count, and then we're going to do some stuff and enter this for loop here. Using what we know so far, we can now use a reduction operation because we are repeatedly adding the result of f of x to our variable called approx. We can use a reduction clause for that. So we don't need a critical section anymore. And then we can calculate the approximated area from that. So the line of code that we add here is pragma OMP parallel for num threads thread count reduction plus approx. And that's all it takes to parallelize this program. And this works, but there's a little subtle bug in here that we have to address, though. So, to demonstrate that, I am going to try this out. So here is our sequential program with absolutely no parallelism at all. I'm going to save that, and then I'm going to clear that. I'm going to clear all this so I can then compile this program. Okay, it works. I'm going to run this with just that because it's not looking for any command line arguments that says I want to run this with some number of threads. So I can just type in /program name, and now I can start typing in my endpoints and the number of trapezoids. Let's start with a obscenely small number of trapezoids. The area becomes more accurate the more trapezoids that we add. But let's just start off pretty simple. Remember that the function is f of x equals x squared. In your last assignment, I had you change that to be whatever function you want. Let's just go back to the f of x equals x squared for the sake of simplicity, and we're going to find the area from endpoints 0 to 10 using only 10 trapezoids. This is not going to be accurate, but that's okay. We're going to do it incorrectly, correctly. So 0, 10, and 10, and now we have an area of 335 units. Oh, for fun, I'm just gonna run it again and see what happens if I do 10, 0, 10. And it gives me the same thing, except I went backwards and it gave me a negative area. So it's working, but incorrectly. So let's try it once again, just to make sure we have a baseline. So we are finding the area under the curve from endpoints 0 to 10, and we only use 10 trapezoids. That gives us an area of 335. Keep that in mind. Now, what we're going to do is I'm going to copy this, and I'm going to rename it to trap P. That means trap parallel. I'm going to open this, and now I'm going to modify the program. I'm going to modify the program using the modifications described in the past few slides. So I'm going to add in a thread count here. Int thread count. I'm going to parse the thread count from the command line arguments. So here we go. Thread count. And thread count. And int thread count equals str toll it was str toll. Thread count str toll argv 1 null 10. There was one error in the slides, and it is this. I miswrote it as thread count being a function somehow. That is incorrect. I have to go fix that. Okay, the slides are fixed. So it is thread count equals str toll argv1 null 10. So with the rest of the program here, we are changing the trap function so it accepts 4 arguments. We are adding str toll to our main function, and then we're passing thread count into our trap function. Within the trap function, not much is changed except for adding a few directives. So that is as follows. We're gonna add in that thread count. There we go. We're gonna add in, for debugging purposes, and you'll see why, int my rank. And now, here's where it gets fun. Pragma, OMP, parallel for. This is enough to parallelize a for loop, but there are a few things we have to do as well. We're going to tell it how many number of threads we want to run this with. So, num threads thread count. We're going to also specify a reduction operation. So, we are going to add in our reduction clause. That operation is addition, and we are applying it to approx. I'm also going to add the following for debugging purposes. So that is my rank, which I just previously added up here, equals OMP get thread null. This is so I can see what each thread is calculating. So this is just calculating the x values. So this is just the thread calculating an x value that it's going to then pass into f of x. So thread d of d has calculated x. That's going to be passed into f of x. So you don't get to see the f of x though. But given that the function is simply f of x equals x squared, you can probably imagine calculating it by hand or with a calculator. It's just x times itself. So we're going to pass in my rank, thread count, and x. We already have my rank being calculated from this. We already have a thread count being passed in, and we already have x being calculated out here. So yeah, this should work now. Okay. Open up. There we go. There we go. So this is now trap P, the parallelized trapezoidal rule function. So clear. I want to compile now trap P. Okay, it worked. / trap P, and it's segfaulted because I did not specify a thread count. So let me fix that. I'm gonna run this with 10 threads and specify the same number of trapezoids and the same endpoints. So 0, 10, 10. It calculated as being 154. That's not good. Let's do it again. Now it's 643. Okay, so there is in fact a bug in here that we're going to fix in a little bit. But I want to discuss what's going on in here by looking at a different program. So, also as a proof of concept, I'm just gonna try it with 5 threads and see how well it works with that. Just proof of concept that this program really is working with any arbitrary number of threads. So, same endpoints as before. And okay, so now we know that it's working with any number of threads, because if you look closely here, there are 5 threads and they're each doing 2 calculations each. Whereas previously it was 1 calculation per thread. So yeah, it is working, but it's almost working. So let's discuss what happened. Or rather, we're gonna discuss a few caveats regarding parallel 4. And it is the following. Okay, so the parallel 4 directive is as follows. We add this directive right before a for loop, and that will parallelize the for loop. So what happens is this. The for loop is partitioned by blocks of size m over t, where m is the number of for loop iterations and t is the number of threads. So by default, the work of the for loop is divided by some number of threads, such that the first thread gets the first m over t partitions, or for loop iterations, and the next thread gets the next m over t partitions, and the next thread gets the next m over t partitions, and so on. We can change that, by the way. I'll show you that in a little bit. So before we continue with bug fixing, I need to talk about a few caveats regarding parallel 4. Because there are some for loop forms that OpenMP cannot parallelize. OpenMP cannot parallelize do while loops or while loops. OpenMP cannot parallelize for loops whose number of loops cannot be determined. OpenMP cannot parallelize for loops that have a break in the loop. Also, it cannot parallelize an infinite loop. OpenMP can only parallelize for loops that are in canonical form. So we have a defined start value, we have a defined end value, and increments only happen in this part of the for loop. So the increment step of the for loop. Basically, for loops only. The start and end values are defined, and they never change throughout the for loop's execution, and increments can only happen within the increment step of the for loop, and no breaking out of the loop. If any for loop fails to meet these conditions, it's going to be rejected by the compiler. That said, it is possible to parallelize a for loop that shouldn't be parallelized. We're going to look into that a little bit, but here's an example of a for loop that cannot be parallelized. This is a linear search code where we have a for loop. So it's iterating through some array of integers, finding some value within. It's going to return the index corresponding to some value in that array. So it's gonna search. If it finds it, it's gonna break out of the loop, and that's the problem. It broke out of the loop. I just said OpenMP cannot parallelize loops that have a break statement. So this cannot be parallelized. If you try to do it, it will throw an error. That said, there are for loops that the compiler can parallelize, but really shouldn't. So here's an example of that. And I'm going to have you write this as well. just for demonstration purposes. This is a for loop for calculating the first 40 Fibonacci numbers. So there is a loop carry dependence in here. And here's what it is. The Fibonacci numbers is a sequence of numbers where the next term in the sequence depends on the value of the previous two terms in the sequence. We start with two initial values of 0 and 0, or 1 and 1. And the next term is going to be, if we start with the initial values 1 and 1 in our sequence, that means the next value is going to be the sum of those two values. So we have 2. The next value is 3, which is 1 plus 2. The next value is 5, which is 2 plus 3. The next value is 8, which is 3 plus 5, and so on and so forth. And this thing grows exponentially it grows exponentially. And the ratio of the last number and the next number is a special value that we call phi, that is like 1.618. So it grows at a rate of 1.618 times larger than the last value. So this is exponential. The loop carry dependence here is, as I said, the next number in the sequence can only be calculated from the last two numbers in the sequence. So let's try to parallelize that. So I have already written the program here ahead of time. Let's just take out this line of code here. So now we have fib.c. This program calculates Fibonacci numbers. Let's try it out. I am going to get this compiled. So fib.c. There is an unused variable. We're gonna ignore that for now. Oh, by the way, if you get warnings like this, you can safely ignore them for now. All the warnings do is tell you how to write cleaner code. So if you get warnings but it still compiles, you're probably good. But it's a good idea to heed the warnings so you write better code that way. So /fib segfault, because it was expecting a command line argument, that is the thread count. Even though we're not using the thread count at all, I'm gonna say run with 10 threads, even though those aren't gonna be doing much of anything. So this is the serial Fibonacci numbers program. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on and so forth, stopping right before it does an integer overflow. So yeah, those are all the Fibonacci numbers from 1 to right before it results in an integer overflow. So what happens when we try to parallelize it? So I'm gonna add back that pragma OMP parallel line. So now we're gonna pass in a thread count and see what happens. I'm gonna recompile the program, and now I'm going to run this. Let's try with one thread and see what happens. Okay, it works the same as before. I can repeat it several times. And it's working the same as before. Clear. Let's do 2 threads. Okay, it works fine as before. Nothing seems to be wrong yet, but let's try it again with 4 threads. Hey, look at that. We got 0. So that's because one of the threads started to add values when it wasn't supposed to. It added values before it had values to add, and it gave us incorrect values. And depending on the order in which these threads execute, we might have several parts of the program be zeros, or worse, they could be garbage values. So I'm gonna try this again with 10 threads, and look at that. It really broke now. Oh, and that really broke now because we got negative values. So I guess it was adding whatever values were already in memory, and they happened to be negative, or they overflowed. So yeah, oops. We should not parallelize this program. My point is, as magical as it sounds to parallelize programs, it is the case that some programs cannot be parallelized for all sorts of reasons, and this is one of them. Loop carry dependencies are one of the many reasons that some programs cannot be parallelized. Okay, so let's get back to the slides and continue our discussion. So really the main thing to be aware of is those loop carry dependencies. This for loop, for example, has a data dependence where yi requires xi to be calculated. But it's not a loop carry so there is a data dependency here, but it is not a loop carry dependency. Basically what that means is we cannot swap the order of xi and yi being calculated, but no part of that for loop requires that the next value be calculated from the previous value. So nothing about yi needs yi minus 1. Nothing about xi needs xi minus 1. So we have a data dependence, but it's not a loop carry dependence. Let's look into how we can write that pi estimation program from pthreads. From our discussion on pthreads, we wrote a pi estimating program. I am not asking you to write this again in OpenMP, but I'm just going to show you what that would look like. So, we have the pi estimation program from pthreads that we are now going to write, or at least we're going to see how it would be written using OpenMP. So, this is the code we can use as a starting point. This is all serial code, even though it takes in a thread count that does nothing right now. We can add in a pragma OMP parallel directive in here, and then we can also add in a reduction clause that basically has it so that because we are adding this here, we are repeatedly doing addition on our variable called sum. So this is a reduction operation happening with a reduction variable. Thus, we can add a reduction clause here. So pragma OMP parallel for num threads thread count reduction plus sum. If you look closely though, we do have a problem, and that is there is a loop carry dependency, and that is on the line for factor here. Factor, the value of factor starts as 1, but because of how this is programmed, every other for loop iteration has factor be -1. This is a loop carry dependence because of how factor is calculated. It becomes negative for the next for loop iteration. So if we don't do this in the right order, we're gonna get the wrong value for pi, which is exactly what happens here. So I calculate the value of pi to be, we expect it to be 3 point whatever, but it calculated as 2.9 and 5.8. That is horribly, horribly wrong. So the problem is that we need to take out this loop carry dependency. So factor equals negative factor is a loop carry dependence that is setting us up for trouble if we try to parallelize it as is. However, what we can do is swap that out for something that uses modular arithmetic. So basically, we know that every other value in the sum must be negative. So we can just use some basic modular arithmetic where k is k is from the for loop here. So it was obscured by the blocks here. So okay, so we are exponentiating -1 by the value of k. But we don't have to do that exponentiation at all. All we really got to do is do some modular arithmetic and say if k was divisible by 0, we say that factor is +1. Otherwise, we say that factor is -1. So that's just basic modular arithmetic. We've just eliminated our loop carry dependence. We can now calculate whether our term is positive or negative without having to use a loop carry dependence. There is a little bit more, however. Note where factor was declared. Because we declared it way out here, this makes factor a shared variable. If we really want to truly, once and for all, eliminate any sort of dependencies, we must have every thread have its own copy of factor. In this code here, all we gotta do is add an extra clause to our directive, private factor. This makes it so that every thread has a private copy of the variable called factor. And if we do that, then we should have absolutely no loop carry dependencies. That means every time you run this program, it will calculate the same value every single time. We can use this information to fix up our trapezoidal rule program. So when we run this program a few times, we find out that it is calculating the wrong value for the area under the curve. And sometimes horribly off too. 663, 670, 74. We know it was 335 from when we tried this using one thread. Let's fix it. Clear. And now let's go back to app P. So all we gotta do is to fix this up is add private X. Also, to be on the safe side, because I declared my rank to be outside over here, I'm just gonna put my rank here in too. So now every thread, when it runs that parallelized for loop, it's gonna have its own private copy of X and its own private copy of rank. So what was happening is, because X was a shared variable, it was being overwritten by all the other threads. Every thread was trying to calculate X, and it was being overwritten by every other thread. That's why the area was being screwed up, and we were getting the wrong area every single time. Race conditions. Okay, so now that should fix it up. Let's see what it looks like now. I'm going to recompile the program, not fib, but rather trap p. Recompile that program. It should work now. /trap p. I'm gonna run it with 10 threads, and I'm gonna run it with endpoints 0, 10, and 10 trapezoids. There we go, 335. If I run it again, 0, 10, 10, 335. Run it once more, 0, 0, 10, 10, 335. And we see that every thread is doing work. If I did this with, say, 6 threads and do 0, 10, 10, then we can see that every thread is doing work. It's just that some threads are doing slightly more work than others. That's because 10 divided by 6 does not divide 10 evenly, so due to the pigeonhole principle, we have a few threads doing a little extra work. That's okay. But this thing called load balancing is something that we have to consider when we're doing larger workloads. It's exactly as it sounds. We want to have each thread do roughly the same amount of work, but with cases like this, it is so small that it's really not a big deal. So yeah, we fixed our program. It's fixed. We did it. Okay. There are a few more things that I would like to talk about. Okay, so it turns out there were 2 ways to fix it. I found that just by declaring the variables inside the for loop, that was also enough to fix it. Let's just roll with what the textbook has us try out, and that is the making our variables private by adding this private clause here. So yeah, there are really 2 ways to do it. So this is going to be your next assignment. I'm going to have instructions for that sometime, hopefully tomorrow. where basically you are going to write the trapezoidal rule program as a serial program, and then you're going to parallelize it with parallel 4, and then you're going to fix that up with the private keyword. And then you're going to try out parallelizing the Fibonacci numbers program and see how it would not work at all. Okay, so those are the bugs that we have finally addressed in the trapezoidal rule function. Now it will work, period. Okay, so there are a few more things that we have to talk about with OpenMP as well. So we're still not done. What if we have nested for loops? So bubble sort is another sorting algorithm that features a nested for loop. The outer for loop finds the largest element in an array and moves it to the last position. Then it finds the second largest element in the array and moves it to the second last position, and so on. The net effect is that the largest elements bubble up to the top. If you go to YouTube and look up sorting algorithm visualizations, you'll find all sorts of visualizations of all the different sorting algorithms out there. Okay, so now we have a nested for loop that describes how bubble sort operates. Can we parallelize it? Well, the outer for loop changes the state of the array by having the largest elements bubble up to the end of the array for each for loop iteration. So there is a loop carry dependency here. In other words, we cannot do the steps of the outer for loop in any order. It must be done in order. Can we parallelize the inner for loop? Well, the inner for loop has a sequence of steps that also cannot be done out of order. It must compare pairs of consecutive elements from beginning to end. This is another loop carry dependency. The outer for loop has a loop carry dependency. The inner for loop has a loop carry dependency. Therefore, we cannot parallelize bubble sort, period. There's another sorting algorithm called odd-even transposition sort. This also has nested for loops. So maybe you've never seen this be done before. Maybe I'll just have to share a video of it being visualized. The algorithm does 2 sets of swaps in succession. Every other element swaps. Okay, so every other element swaps with the element to the left if they're out of order. Then every other element swaps with the element to the right if they're out of order. By every other element, we mean the odd index elements. So we have 2 different for loops, but only one of them is ever executed. So check this out. If phase is for determining whether we're doing the swap to the left or the swap to the right. We're only ever executing one of the 2 for loops, never both of these at the same time. So basically, we will only ever need to worry about one of these 2 for loops. So it's basically the same as a doubly nested for loop. The outer for loop governs which phase of the inner loop we're doing. We're either swapping to the left or swapping to the right. So we're doing either the even phase or the odd phase. The algorithm works by alternating between even and odd phases using the outer for loop. What that means is it must be even and then odd, and then even and then odd. Even phase, odd phase, even phase, odd phase. We cannot do the outer for loop in any order we want. That is a loop carry dependency. We cannot parallelize the outer for loop. Can we parallelize the inner one? And the answer is yes. Basically, what's going on is this. For the swaps, an element is swapping with the element to the left or the right. Basically, it's doing a swap with its neighbor. But the thing is, a swap with its neighbor does not affect the swap with some other threads. An element swapping with its neighbor does not affect some other element swapping with its neighbor. Which means we can do these swaps in any order we want. That means we can do these swaps in parallel. Also, these swaps are only ever done to like one element swapping with, yeah, so the swaps only ever happen with an element and an adjacent element. My point is where we can parallelize the inner for loops. It turns out there are a few ways we can do this as well. So the first solution is to add the following directives before each inner for loop. So this is the full directive here. Pragma OMP parallel for num threads thread count, default none, shared AN, private I, TMP. So the first solution will have the outer for loop execute the inner for loop. The inner for loop then forks, executes the loop, and then joins. Then the outer for loop advances to the next loop iteration and does it again. However, it's doing a fork and join for every iteration of the outer for loop. Each fork and join operation adds time to our execution time. So basically what's going on is this. It doesn't matter which phase we're doing because every phase has a fork and join. So we're doing the even phase. We do a fork, we execute some code, and then we do a join. And then we do the odd phase, where we fork, do some stuff, and then we join again. Every time we do a fork and join, that adds overhead. Can we reduce that overhead by doing a fork but before we do anything, and then do the cha-cha slide? And the answer is yes. Here's the other solution. So Pragma OMP parallel num threads thread count. That forks the main thread into a team of threads before we do anything with the for loops. So it basically separated the singular Pragma OMP parallel for into two directives. The first one is fork the main thread into a team of threads. The second one is, okay, let's get together and work on this together. So now, we fork before we even enter the for loop to begin with. But the program's smart enough to know that when to work with a team of threads. So this creates a team of threads before we even need the team of threads. This is the second solution to the odd-even transposition sort. The second solution will have the outer for loop execute the inner for loop. But before it even does that, the program forks into a team of threads. This doesn't parallelize the outer for loop. Rather, all the threads are right there on standby, waiting for when it's go time to execute the parallel sections. That is the Pragma OMP 4. Basically, we're doing only one fork operation and one join operation. We fork before we even enter the for loop, and we join after we've done the whole for loop. The program forks into a team of threads. That team waits for the inner for loop to execute, which is run in parallel. That way, we use the same team of threads throughout the execution of the whole algorithm. We don't do a fork and join for every for loop iteration. That saves on time. And it makes our programs even more efficient. Because parallelizing code introduces some oddities, such as the time it takes to fork and join, and in some other cases, we realize that some programs cannot be parallelized at all. Those are just some things we have to keep in mind when we parallelize certain programs. Okay, so the last part of this is, how does the program, what does it look like for the program to schedule for loops to threads? So, scheduling for loop iterations to threads. So we had a hint of what that looked like when we were running our trapezoidal rule program, where some threads get certain for loop iterations and so on and so forth. Several slides ago, I mentioned what that was like, and that is described in typically, so by default, the partitioning is done by blocks. For M partitions and T threads, the first thread gets the first M over T partitions, the next thread gets the next M over T partitions, and so on and so forth. Some concessions have to be made if M over T does not result in an integer solution, but basically this program is smart enough to distribute these for loop iterations among all threads, even if it isn't perfectly divisible. So let's look at that scheduling. So you could write this program to see how the program assigns for loop iterations to each thread. You can write this in your own time. This isn't really its own assignment, it's just there for demonstration purposes. For example, if the for loop had 100 loop iterations and we had 4 threads, then each thread gets 25 for loop iterations. Thread 0 gets the first 24, thread 1 gets the next, 25, because this is all 0 indexed. Thread 0 gets the first 25 iterations, thread 1 gets the next 25 iterations after that, so on and so forth. Generally, if there are n iterations, the first n over thread count iterations are assigned to thread 0. The next n over the thread count iterations are assigned to thread 1. Are there situations where this assignment is not optimal? Suppose we wanted to parallelize this code and the time required to call the function f is proportional to the size of the argument I. This means using block partitioning, more work will be given to thread 0. To better distribute the work, we can try something else, like cyclic partitioning round robin. The schedule clause allows us to change the default scheduling of OpenMP to something else. And your options are static, dynamic, or guided, and auto, and runtime. So here's the clause here. The type can be static, dynamic, guided, auto, or runtime, and we can also specify a chunk size. So by default, so the chunk size is a positive integer that denotes how large a chunk is. So by default, our scheduling looks like this. If we say schedule static 2, that means, so by default, our scheduling looks like this. If we say schedule static 2, that means each chunk is going to do 2 for loop iterations at a time. So thread 0 does 2 iterations, thread 1 does the 2 iterations after that, thread 2 does the 2 iterations after that, thread 3 does the 2 iterations after that, and then it cycles back to 0. So we have this staircase looking pattern here. Only static, dynamic, and guided schedules have a chunk size. The static schedule type assigns chunk size to each thread in a round robin fashion. So this is actually round robin. Yeah, so this is basically round robin, and I realize it's been cut off my webcam, but basically this is round robin scheduling. If you look at the next slide, the static schedule type assigns chunk size to each thread in a round robin fashion. Changing the chunk size to 1 gives us round robin behavior, but as you saw in the previous slide, that could be any value. Omitting a chunk size will, in most implementations, default to a chunk size of iterations over thread count. So basically, the default. This is the default. We can change the chunk size to get round robin schedule. And again, you can play with that program if you want to see the different types of scheduling. In dynamic scheduling, iterations are broken up into chunks of chunk size. Each thread executes a chunk, and when a thread finishes a chunk, it requests another one from the runtime system. New chunks are given to threads on a first-come, first-served basis. This can be advantageous if loop iterations don't take a uniform time to complete. However, since the ranges are not allocated ahead of time, there is some overhead with assigning chunks at runtime. The guided schedule is similar to a dynamic schedule, except the chunk size shrinks each time a chunk is completed. The sizes of chunks decrease down to what chunk size is. If not specified, the chunk size decreases down to 1. The guided schedule is useful if later for loop iterations are more computationally expensive. So which schedule do you use? Well, it really depends on what you want. 2 things come to mind. What scheduling type to use? How big is your chunk size? A few things to keep in mind. There is some overhead with using the schedule clause. However, using a dynamic schedule has greater overhead than just using a static clause. And using a guided schedule has even more overhead than using a dynamic schedule. If you feel like you're getting satisfactory results using the default schedule, don't worry about scheduling at all. But if you suspect that default scheduling just isn't enough and you feel like you can improve it, then try it out and see if you can get it to work better. Here are some situations where it is useful to consider different schedules. If each loop iteration takes roughly the same amount of time, default schedules should be okay. If the cost of iterations increases or decreases linearly as the loop executes, then you may want a static schedule with a small chunk size. If the cost of iterations cannot be determined in advance, try a runtime schedule. So yeah, that's it. That is everything that I wanted to talk about for OpenMP. Your next assignment is just going to be to try out the parallel for directive and parallelizing a for loop that should not be parallelized. So, all this should be updated on the canvas within the next several hours by the time you watch this, or it may be updated by now by the time you watch this. But yeah, this is everything I wanted to talk about OpenMP. Your next assignment is just going to be try out the parallel for directive with the trapezoid rule program. And then finally, after all that, we can cycle back to MPI. So MPI is even more interesting. So we'll have to see what that looks like later on. All right, take care, and I'll see you in the next video.